When most people imagine Yellowstone's last supereruption, they picture one impossible moment. A giant magma chamber ruptures beneath the ground. An enormous explosion tears open the landscape, and hundreds of cubic kilometers of volcanic material erupt almost at once. But the rocks inside Yellowstone are now telling a different story. New field evidence suggests the eruption that formed Yellowstone Caldera about 631,000 years ago may not have been one single catastrophic blast at all. Instead, it appears to have involved multiple magma bodies, multiple vents, and a sequence of separate eruptions. Some deposits had enough time to cool and solidify before later explosions ripped them apart and erupted them again. And the new evidence may even force scientists to redraw a part of Yellowstone's caldera itself. The discovery comes from Sour Creek Dome, a broad, elevated region just north of Yellowstone Lake. For decades, geologists thought they understood what this feature represented. Sour Creek was classified as a resurgent dome, a region supposedly pushed upward after the giant caldera-forming eruption as magma re-injected beneath the collapsed landscape. That explanation seemed reasonable. Yellowstone's youngest caldera formed during the Lava Creek Tuff eruption roughly 631,000 years ago. After such a massive evacuation of magma, the ground collapsed, creating a huge depression. Later magma beneath the surface could have pushed part of that floor upward again. But several years ago, scientists dated rocks inside Sour Creek Dome and found something unexpected. Some rocks previously thought to be much older were actually almost exactly the same age as the Lava Creek Tuff itself. That result created a problem. If these rocks were not ancient material simply lifted upward after the eruption, then what were they doing there? Over the next 5 years, geologists returned to the area and began remapping the rocks in detail. This was not easy terrain. Sour Creek Dome contains dense lodgepole pine forest, fallen trees, boggy ground, and difficult access. But scattered through that landscape were layers of volcanic rock preserving clues from one of the largest eruptions in North American history. And those layers did not look like the aftermath of one instantaneous explosion. Researchers identified 5 previously unrecognized packages of ignimbrite. Ignimbrite forms when incredibly hot mixtures of ash, gas, pumice, and rock race across the ground during explosive eruptions, and then settle into thick deposits. The 5 packages all produced ages averaging about 631,500 years, essentially indistinguishable within dating uncertainty from the Lava Creek Tuff eruption, yet physically they were different. Some contained different amounts of pumice or scoria. Others contained noticeably different crystal populations. Most importantly, several layers contained fragments of older volcanic material that had already cooled and hardened before becoming incorporated into a later eruption. That one detail changes the sequence dramatically. Imagine an eruption deposits a thick layer of hot ash and volcanic debris. If another pulse happens immediately while everything remains hot and mobile, the material can mix together. But if fragments from the first deposit later appear as solid broken pieces inside another deposit, then the earlier layer must have had time to cool, become rigid, fracture, and then be torn apart. The Yellowstone rocks therefore contain a geological timestamp that radiometric dating alone cannot provide. Scientists still cannot determine whether the pauses lasted days, weeks, months, years, or even longer. The radioactive clocks in the crystals simply do not have enough resolution at this age to distinguish those short intervals, but they can say something important. The eruption was a sequence. Previously, the Lava Creek Tuff was commonly divided into 2 major eruptive members, called A and B. The new mapping at Sour Creek suggests the real history was considerably more complicated, and then the crystals revealed another surprise. The researchers analyzed sanidine, a potassium-rich feldspar mineral commonly found in Yellowstone's rhyolitic volcanic rocks. Sanidine is useful because scientists can date it using argon isotopes, but its chemistry also preserves information about the magma in which it formed. If all of these eruptions came from one enormous, well-mixed magma chamber, scientists might expect many of the crystals to share broadly similar chemical histories. Instead, the newly mapped deposits showed distinct compositional signatures. The evidence indicates that at least 4 separate magma bodies contributed to the eruption sequence. Some appear to have received injections of hotter magma shortly before erupting. others seem to have evolved more quietly for longer periods. This replaces the simple image of one giant underground tank with something more like a network of magma pockets, each with its own history. And remarkably, that picture resembles what geophysical imaging suggests beneath Yellowstone today. Modern studies do not show one vast cavern filled completely with liquid magma. Magma beneath Yellowstone exists largely in partially molten regions containing smaller concentrations of melt. The new geological evidence suggests that similarly distributed magma bodies may also have played a major role during ancient caldera-forming eruptions. But Sour Creek Dome produced an even stranger clue. For decades, maps placed the eastern boundary of Yellowstone Caldera roughly 16 kilometers, or about 10 miles, east of some of these newly studied deposits. The rocks themselves now challenge that geometry. Many deposits contain abundant recycled volcanic fragments, but very little older crustal rock. Based on their textures, researchers argue that several eruptions probably originated from vents only a few kilometers away. If the eruptions had come from the traditionally mapped ring fracture 16 kilometers to the east, the deposits should tell a different story. Instead, the evidence suggests that some vents may have existed much farther inside the traditionally mapped caldera, potentially along a zone close to the modern Yellowstone River between Yellowstone Lake and Canyon Village. That could mean the accepted outline of the youngest Yellowstone caldera needs to be revised. The caldera may have been somewhat smaller and more circular than maps currently show. Even Sour Creek Dome itself may need reinterpretation. The feature has long been described as a resurgent dome, created when the caldera floor was pushed upward after collapse. But high-resolution LiDAR mapping allowed researchers to examine the faults crossing the dome with far greater precision. The ages of those faults created another contradiction. Some faulting appears to be almost 500,000 years younger than the Lava Creek Tuff eruption. That makes it difficult to explain the entire dome as an uplift structure formed immediately after caldera collapse. Instead, the researchers propose that Sour Creek Dome may largely be constructional. In other words, rather than the ground simply rising from below, repeated eruptions may have progressively piled volcanic material into a broad dome-shaped feature. One eruption deposits a layer, another eruption adds more. Later pulses build additional packages on top. Hundreds of thousands of years of erosion then obscure the original architecture, leaving geologists to reconstruct the sequence from scattered exposures. This is important for more than just Yellowstone. The word supereruption can create a misleading mental image. Humans naturally imagine large disasters as single events, one earthquake, one explosion, one impact. But very large volcanic systems do not always behave that way. Yellowstone's older Huckleberry Ridge Tuff eruption, about 2.1 million years ago, has also produced evidence for multiple eruptive phases and multiple magma bodies. Some studies suggest pauses during large caldera-forming sequences can range from hours to much longer periods. That means a supereruption may sometimes be better understood as an eruptive episode rather than a single instant. The total amount of material can still be enormous. The consequences can still be catastrophic, but the pathway from an intact magma system to a collapsed caldera may involve several reservoirs failing at different times, new vents opening, deposits cooling, magma recharging, and later explosions recycling material erupted earlier. That distinction matters when scientists try to reconstruct how the largest volcanic systems work. It may also matter for interpreting warning signs. This new study does not mean Yellowstone is preparing to erupt now. The Yellowstone Volcano Observatory currently reports normal background volcanic activity. A new interpretation of a 631,000-year-old eruption is not evidence of an imminent eruption. What it changes is the model scientists use when thinking about how huge eruptions develop. If ancient supereruptions involved multiple magma bodies rather than one giant reservoir, then future studies need to understand how those separate bodies interact. Does one eruption destabilize another reservoir nearby? Can magma recharge between eruptive pulses? How quickly can the plumbing system reorganize after part of it erupts? The rocks at Sour Creek cannot answer every question, but they preserve something unusually valuable: the sequence of events. One deposit formed, it cooled. Later volcanic activity shattered parts of it, another eruption buried those fragments. Different crystals record different magma histories, different packages point toward different sources, and faults once thought to explain the dome appear to have formed far later than the eruptions themselves. Piece by piece, the simplest version of Yellowstone's most recent supereruption has fallen apart. The replacement is more complicated, but also more realistic. About 631,000 years ago, Yellowstone may not have exploded once. It may have erupted again and again from several magma bodies and several vents over a span of time that the rocks can reveal only indirectly. And hidden in a forest north of Yellowstone Lake, those rocks are now forcing scientists to rethink not only how the eruption happened, but even the shape of the giant caldera it left behind.